Hi there, welcome to Monash Open Day. I'm here to tell you about how, what and why I think about maths. My name is Norm Doe and I'm a senior lecturer in the School of Mathematics at Monash University. Part one of my talk is where I tell you about the only topic on which I'm the world's foremost expert. What do you think that might be? Now, it's not going to be some part of mathematics, but actually it's going to be about me. Pretty much the only topic I can really sort of claim to be an expert on. Now, the reason why I want to tell you this is because I think if anyone tells you anything, you need to know who they are. For instance, if a head of state, for instance, with no credentials in the health sciences decides to tell you about their cure for COVID-19, maybe don't believe them as much as your trained medical practitioner. Anyway, my story begins, as most people's stories do, when I was born. And I'd like to tell you as a child that I quite enjoyed mathematics. Now, before you think that's a little bit strange, I'm here to claim that actually this is just the natural state for humans to love mathematics. If I think, for instance, about young children, in particular my own 6-year-old and 3-year-old, and what they love to do, I see that they love numbers. They love playing with ideas. They love playing with shapes or creating things with Lego and blocks. They love asking questions about the world and discovering new things. And I think this is the true spirit of what mathematics is. And somewhere along the way during school, a lot of people, for one reason or another, somehow lose that love of mathematics. So I'm here to remind you exactly what maths is about. Now, that was me as a child. I'd like to fast forward to me when I was finishing school, because many of you are at that stage right now. And I'd like to tell you about how I ended up choosing my university courses. You see, I progressed through school enjoying mathematics most of the way, and I knew when I finished school that I still loved mathematics. So I thought I'd do a science degree where I could really satisfy my passion to discover more about maths. But I thought I'd do something else as well, and I was quite interested in the arts and the humanities. So being passionate about these two things, I thought a combined degree in the arts and sciences would suit me well. So is that what I ended up studying? As it turns out, no, because this is what happened. On the night before my course preferences were due, I had a very concerned mother of a friend of mine call me up and desperately pleaded with me not to study mathematics. She said, "Don't do this, Norm. You're throwing your life away. You'll come out of the end of your degree and not be able to get a job. Or maybe you'll be able to get a job, but it'll be something like a high school mathematics teacher." Now, how wrong she was. And I didn't know at the time because I was young and naive, but I do know now. Doing a degree in mathematics places you very well for a career. And if that career happens to be in high school mathematics teaching, then I think that's a particularly noble thing to do. And some of the happiest people I know are high school mathematics teachers. Anyway, she said to me, if you're really keen on doing maths, at least do an engineering degree on the side, forget about the arts. And silly me, it turns out that I listened to her. So actually one of my pet peeves now is to hear students say things like, I like maths, so I'm going to do engineering. What I think people should say is, if they love engineering, they should do engineering. But if they love maths, maybe think about studying mathematics. So I persisted with my engineering degree. It's not something that I use today. As I said, I'm now a senior lecturer in the School of Mathematics. Now let's fast forward to my job now. What do you think I do as a senior lecturer at the university? You might think I spend all my days lecturing, and actually that's not quite the truth. You see, my job entails about 1/3 teaching and lecturing, about 1/3 doing mathematics research, and about 1/3 checking my emails, because almost any job today involves a lot of that. Now, I won't tell you about the teaching or the emails, but I'll say something about the research, because that's something that most people don't know too much about. You see, when I say meet people at a party, or if I'm talking to the person next to me on a plane, or if I'm talking to the taxi driver taking me to the airport, and they ask me about what I do, and I tell them that I do maths research, most of them don't know what that means. If they push me further to ask, well, what does that entail? I'd say, well, it really means that I'm trying to create new knowledge in mathematics. I'm trying to solve new problems in mathematics. For a lot of people, their first reaction is, well, wasn't there enough already? And I claim not. Maths is a very expansive discipline. There are still so many things we don't know, and it's a real joy, and it's very satisfying to be part of a community which is trying to develop this new knowledge. Anyway, maybe that's enough about me for now. Let's move on to part 2 of my talk. In the next part of my talk, I'd like to tell you what maths is about and how school maths is only really the tip of the iceberg. We're going to ask the question, what is maths? Now, if you want to know what maths is, in fact, if you want to know anything in this world, what do? Of course, the first thing you do is you go straight to Wikipedia and you type in maths. And what does it tell you? Well, Wikipedia claims that maths is about 3 things. First, studying quantity, structure, space, and change. Second, it is about seeking out patterns and formulating new conjectures. And third, it is about resolving conjectures by mathematical proof. Now, my claim is that in school, we don't actually see the whole diversity of mathematics. In fact, really out of these 3 things, we spend most of our time in school mathematics learning only spending time on the first. Yes, we do study quantity in the form of numbers, structure, space in the form of geometry, and change, which essentially relates to things like calculus that you might be learning about. But we spend very little time on seeking out patterns and formulating new conjectures, and very little time on resolving conjectures by mathematical proof. So my claim is that the real essence of mathematics isn't fully portrayed by our education at school. Now, of course, Wikipedia is all well and good, but if you want an alternative but equally reliable source of knowledge, you could ask Norm, that's me. So what would I say maths is about? Well, I'd say it's about these 3 things. First, solving concrete problems. Second, playing around with ideas. And third, analysing problems beyond their solution. And again, I claim that we don't do much of these things in the school setting. So I should be clear about what these things mean. When I say solving concrete problems, well, I mean that the problems have to be in some sense a little bit explicit. If you just said, well, I want to solve the problem of world peace, then possibly maths, it's not so clear how maths has something to say about that problem. That's not to say that it doesn't, but maybe you'd have to sort of refine your problem and look deeper into it and make it a little bit more concrete and explicit before you can bring your mathematical knowledge to bear on that problem. When I say solving concrete problems, I also don't mean solving problems about concrete, but that is not to say that maths doesn't or isn't able to solve problems you might have with concrete. In fact, I used to have a friend who worked at a concrete company and indeed used mathematics to solve problems there. So maths, I claim, is about playing around with ideas. And this is really what I think the bulk of my job in research is about. I sit there and I think, and I play around and I try and discover new mathematics in that way. And this third one is maybe something that people don't talk about much, but the spirit or the nature of being a mathematician is to analyze problems beyond their solution. As soon as you solve one, of course, you sit there patting yourself on the back. But the next thing you do is you ask, well, what other problems does this lead to? The tools that I've used in my solution, can they be taken to solve a different, maybe more difficult problem? So as I'm saying, and I'll say it again, maths is more than what you see at school. And you might ask, well, why is that? And one of the reasons is that the school maths that we do is enabling. It's enabling us to do more in mathematics. But if you don't go on to study more mathematics, you never see that. So people often say that school maths is like the vocabulary, the spelling, and the grammar of English. Now, vocabulary, spelling, and grammar are of course very important. They enable you to do useful things like writing letters and creative things like writing stories. School math is very similar. It enables you to do useful things like solving real-world problems that require mathematics, as well as creative things like solving interesting, difficult problems. The issue, though, is that in the school setting, you don't see much of these useful and creative things, which is why, if you really love mathematics, I'll encourage you to go on studying it beyond school. The other impression that school maths gives you is that maths is quite limited, right? That there are only a few topics and that maybe once you've understood those topics, you know a lot of mathematics. And I'm here to tell you that that is certainly not the case. The world of maths is essentially limitless. And to really sort of make the point, if you look at how much new mathematics is being produced every year, there's tons of it. More than 75,000 articles containing new mathematical results appear each year. And as I've said before, as a mathematical researcher, I'm part of the problem. One of the other things that you might think about mathematics is that there's a sense of linear progression through mathematics. And this is what school somehow tells you, right? You start off doing like grade 1 mathematics, then grade 2 mathematics, then grade 3. And maybe if you go all the way up to year 11 and 12, you start to realize, well, maybe there's a little bit of choice in year 11 and 12. But mathematics is way more diverse than that. If you go on to study mathematics at the university level, in particular, if you come to Monash and study with me, there are subjects like calculus and linear algebra, which you learn about in your first year of studies. But after that, the number of topics just explodes. You can go on to do things like statistics, multivariable calculus, group theory, number theory, real analysis, probability, computational mathematics. The list goes on and on. Maybe I've sort of cheated here and suggested that it's an almost infinite list. That's not quite the case. But there are several lines which sort of just don't fit onto my slides here. Okay, well, that's the end of part 2 of my talk. Let's go on to part 3. Now, I know you probably didn't come here for this, but as a maths lecturer, I can't help but try and teach you a little bit about mathematics. So in this section of the talk, I'm going to tell you about some maths, which hopefully you don't already know, and I hope you find it amazing. Now, there are thousands and thousands of things I could have pulled out for this, but I had to choose just one. Hopefully I've chosen something that appeals to everyone, something you can do in your own home. Okay, so what do you need for this? You need a long strip of paper. Okay, now don't run off and get one. It's okay, we'll just do this mentally. What we're going to do is take a long strip of paper, and if you don't have it with you, just do it with your arms. It looks like this, if you can see there. Okay, and what we're going to do is try and fold this strip of paper in half, right, like so, and then unfold that strip of paper, but make that fold 90 degrees. So with your arms, you should be forming something like the Y from YMCA. On my slides, you should be able to see it looks a little bit like this V shape. Now, nothing too exciting there. But let's maybe try and make things a little bit more complicated. What if we took a long strip of paper, fold it in half, then fold it in half again? Okay, and now what we'd like to do is unfurl our piece of paper and make all the folds 90 degrees. This is a little bit hard to do, but you should get something a little bit like this. Okay, maybe instead of looking at me, let's see what the computer says you should get. Something like this shape. Again, maybe you don't think this is terribly exciting, but then let's try it again. And I don't suggest you do this with your arms. If you really want to do it at home, pull out a strip of paper and give it a go. But let me do this for you. This is what the next step looks like. So you can see it's getting a little bit more intricate, but possibly not enough for you to think that this is amazing. But let's just keep doing it. I'll do it a whole bunch of times and we'll see what happens. This is what you get if you could do this 15 times. And I hope you agree, this is not something that you probably would have expected when we started this exercise. We get this beautiful picture, and this thing in mathematics is called the dragon curve or the dragon fractal. You might ask why that is. I mean, I guess if you sort of are a little bit short-sighted, a bit myopic, you might actually think that this looks a bit like a dragon. So that's why it's given that name. And it's a really amazing object. And of course, as you can see, it came about just by this very simple rule of folding again, and then unfurling your piece of paper until all the folds are 90 degrees. Now, I just want to point out some things about this which are amazing. There are many things I could say, but here are a couple of little observations. One, when you do this, your piece of paper, once you unfurl it, will never try to sort of like cross over itself. You know, if it sort of comes and meets itself, then it sort of goes back out again. It never crosses over itself. That's the first thing. And here's another little observation. Let's consider this like as if it was a map, and maybe that this dragon picture that we see is actually an island. Now, if you sort of focus in this sort of in the sort of section, which is, I guess you could call like the sort of back of the dragon, or if you think of this as an island, if you look at these bays that are being formed all over the place, they're quite intricate themselves. And you might recognize that these bays in this island are precisely the same shape as the original island, as the dragon itself. What I'm trying to tell you is that you could take this shape and actually tile your bathroom with it, right? That you could take a whole bunch of these and actually slot beautifully against each other, and you could tile a whole bathroom. Obviously, maybe don't go out and change your bathroom tiles just yet. This is sort of a little bit tricky to actually cut a tile like this. So I think this little mathematical exercise really sort of, I don't know, sort of tells me a little bit about how amazing mathematics can be. It sort of suggests that almost anything that you look at, if you have a very mathematical mindset, can turn out to be interesting, even if it's as simple as just folding and unfolding a piece of paper. Some of you might be studying mathematics right now, and I hope you also continue to do it in the future. So I think it might be a good time to tell you about what I think the right way is to learn mathematics to make it easier and more fun. So let's think about how I learn maths, but also that it also speaks to how I teach mathematics. So let's get one thing out of the way first, and that's the admission that maths is difficult. It's not just difficult for you, it's difficult for me, it's difficult for everybody, and maths problems can be hard. As a famous example, Andrew Wiles, the British mathematician, spent 8 consecutive years working on the famous problem called Fermat's last theorem before solving it finally in 1994. Now, of course, he didn't work continuously without food and without bathing, but he did think pretty hard about this problem before cracking it. Similarly, I've thought about problems for a long time. I've got one at the moment that I've been working on for several months, and I haven't solved it yet, but every time I sit down to give it a go, I feel like the solution's just around the corner. Now, if maths was easy, I claim that it would be boring. The challenge of doing mathematics brings about productive struggle and makes you a better person to just enjoy that struggle and that journey, even if sometimes the solution seems very far away. But even though math is difficult, I claim that you can do it. I've met many people in the mathematics world. I've taught many students at all possible levels, and I've never met anyone I would call a mathematical genius. So you don't have to worry about whether you're a genius or not. You're not. I'm not. No one is. What you just need is the right attitude, a patience for learning mathematics, and a real passion for challenges to really enjoy that struggle. And don't be afraid to be wrong. I must estimate that probably more than 90% of the time when I'm doing mathematics research, I'm probably not writing down something that eventually leads to what you might call the end result in some sense. But actually, a lot of these wrong paths do help you get a feel for where the actual solution lies to a problem. So I said I was going to teach you about how to learn maths. In fact, I lied. I'm going to tell you about how to learn Chinese. So imagine you're given the task of learning all of the approximately 20,000 Chinese characters. A bad way to do it would be to pull out 20 random ones and just try and stick them in your head and commit them to memory. And then on day 2, to pull out 20 more and then just stare at them until they're stuck in your head. And then continue in the same vein in day 3, day 4, etc. Because by day 5, 10, 20, whatever it is, there's no way you've remembered anything. So I claim that what's missing when you're trying to memorize Chinese characters or mathematics, or indeed anything that you're learning, is context and story, because the human brain is built very well for remembering these things. So I think we have to remind ourselves that Chinese was not invented to torture us with memorization exercises, but was invented for a reason. The reason being to communicate in the written form between human beings. Also, not only was there a reason, but it was created somewhat organically. People probably started drawing pictures to represent objects, which then sort of morphed into the characters that we see to this day. So if we take a look at this list of Chinese characters, you see that maybe people drew a man as a full stick figure, as we might do now, but then over time it got shortened to maybe just the legs. This character for big is the man talking about the fish that got away. It was this big. The character for mouth, it was pretty self-explanatory. And the character for say, you see the tongue wagging in the mouth. the character for word, you see the hot air rising from the mouth. That all makes sense. And now there's a context, and hopefully it's much easier to remember, not just 20 random characters, but these characters and the interconnections between them. If we look at the character for tree, well, it sort of looks like a tree. More interestingly, though, is the character for beginning, which is the tree with a little tick mark at the root or the beginning of the tree. And of course, end is the tree with a tick mark at the other side. The character for distress I find pretty interesting because, yes, I would be distressed if I had a tree in my mouth too. Finally, let's look at this last line. Home, we see this frying pan lid at the top, and underneath this other character, the frying pan lid is a roof, and the character underneath, I'm told, is a pig. And so this harks back to the time when people kept domestic animals in or around their homes. Honor is a man standing by his word. And that's not to say that people of all genders can't have honor, of course, but this is just the history and the story as it developed, and it's come to us organically in this way. The character for good has a mother next to a child. So it's saying that the relationship between mother and child is a good one. Peace is sort of funny. We see the, again, this frying pan lid at the top is a roof, and underneath the character for a woman, and quarrel, the character, two characters for women, or two women side by side. Okay, so I didn't invent the language, obviously. This is just the stories that can be used to memorize or to help you to learn these characters. And I think there's a lot we can say by analogy about the way that we should learn mathematics. So first is to ask why and ask it often. Where did it come from, right? What does it mean? Why does it even exist? Also, keep in mind that things are easy to remember when they make sense. So remember the idea behind the mathematics that you're learning, not just the end result. And of course, finally, remember that maths was developed by humans for a reason. If you know the reason, then the maths will definitely make more sense. In this final part of my talk, I'd like to tell you about why I think more people should study more maths, and that certainly includes you, particularly if you're not sure about what career you'd like to have yet. Now, if I told you that I thought that maths is useful, I think you'd probably say that you agree, but I'm pretty sure you don't know the extent to which maths is useful, and I'd like to try and convince you of that now. So let me start with an example, which is the maths of the Google search engine. So everyone's heard of Google, of course, and one of the reasons why the Google search engine is so successful is that when you search for whatever you're searching for, it doesn't just give you a random list of web pages that include your search term. What it does is it ranks these pages based on something called PageRank. Now, you might think it's called PageRank because it ranks pages. Incidentally, that's not the case. It's actually called it because it's named after one of the co-founders of Google, Larry Page. The basic premise of PageRank is that you think of these web pages as somehow dots, and when one web page links to another, you think of an arrow pointing from the first dot to the second. And what PageRank does, it essentially tries to measure the popularity of these dots, or you can think of them as people as you like. And maybe a link is just if someone likes that other person. Now, of course, to be a popular person, not only do you have to have many people who like you, but you're even more popular if those people who like you are popular themselves. And when you take into this account and express it in a mathematical way, what you've done is you've recreated PageRank. Now, I like this example, not only because it's somehow, because everyone knows about it, but because we actually give this to our first year mathematics students at Monash University. We give them a very small toy example of the internet and ask them to implement on a computer the PageRank algorithm. Now, I want to speak about careers, and I could tell you about all the opportunities available to you if you study mathematics, but you shouldn't believe me. Instead, believe the internet. Go to this website, careercast.com, and see what they've written there. You see, last year in 2019, they took 220 jobs and ranked them from best to worst based on 4 factors. The first being the income that you make in that job. The second being the growth outlook of that sector. So how likely you are to get a job now and in the future. The work environment, and finally the stress of being in that job. Now, if you're like me and you know that this list exists, you go straight to the website and you jump to the bottom. You want to know what not to be. And so here are the 6 worst ranking jobs in the list. But what I'm here to do today is to show you what the top 10 looks like. And I claim that most of the jobs in the top 10 require fundamentally mathematical knowledge. So let's start at number 10, which is actuary. If you don't know what an actuary is, it's essentially someone who uses mathematics and statistics to measure risk, and they often work for insurance companies. Number 9 is an operations research analyst. So you may not know, but operations research is a particular branch of mathematics dealing with essentially optimizing operations and processes and so forth. Then we come to number 8, which is mathematician, someone who uses mathematics fundamentally in their job every day, of course. Number 7 is an information security analyst. So as you can imagine, information security is a very big sector, and there's going to be an increasingly big sector going forward. It combines skills coming from mathematics, statistics, and computer science. Then we'll skip a few and go to number 2, which is statistician, obviously someone who uses statistical methods in their job. And number 1 is data scientist. And I'm sure many of you know that data is a sort of very big, the data science industry is a very big sector at the moment and ever growing. And it requires skills, again, from mathematics, from statistics, from computer science and so forth to deal with large data sets. So the internet tells you that if you study mathematics, that's going to set you up for a pretty decent job. But still I find selling maths careers to students pretty difficult. And I think one of the reasons is because maths is a skill rather than a profession. So people know that if you study a law degree, you'll end up as a lawyer. Or if you study an engineering degree, you'll end up as an engineer probably. But math is a bit different to that. Because it's a skill, there are all sorts of different jobs you could end up in if you study mathematics. And I find that this is actually one of the advantages to studying something like maths, because if you go and look at all the sort of jobs available to you now, you probably haven't heard of the vast majority of them, right? And so it's not clear what sort of studies or what sort of degree will set you up to work in that profession. And indeed, maths being a skill means it's widely transferable and applicable. And that's going to be increasingly useful over time as we find maybe in 10 years from now, a lot of jobs that don't even exist right now. So here's just a little selection of, I could have listed probably about 100 jobs that most of which you haven't heard of, and all of which fundamentally require mathematical thinking. So I hope you're at least a little bit convinced that mathematics is a good thing to do. And if that's the case, I'd love to see you at Monash University, where you can study under lecturers like myself. But in the meantime, good luck with everything, and I hope to see you in the future.